samples, yeah? Sorry. So this is sample 3.8, problem 3.8 from our notes. And you can see here that we've got a simply supported beam with two supports. We've got a pin joint here. And technically, we've got the ability to react a horizontal and a vertical load. Over here, we've got a roller support, and that can only, not very straight, I guess, that can only take vertical loads because the horizontal reaction is taken out with movement, okay? So if we did have a force in this direction, yeah, it would get reacted by this RAX at this end. We've got RAY, and we've got well, that's not A, sorry. Let's just call it RX, RY. 1, RX2, or Y2, sorry. It's not a good start. I stayed up way too late last night. Anyway, so if we were to have, we don't have one here, but if we had 100 newtons horizontal, this support here would react any sort of horizontal loading, okay? This guy here cannot take any horizontal load. So the question says, for the beam, reduce the system of forces shown to A, an equivalent force couple system at A, B, an equivalent force couple system at B, and C, a single force or resultant. Okay, so essentially here you've got four, let's clear all of that again. So here we've got four forces. What it's saying is in part A, it says, I want to reduce all of those four forces to one force couple system. So a force that produces a force and a moment that is equivalent to each of those forces being applied. Okay. And then the second one is, I want to do the same, but this time I want to do it at B. Okay, I want to do it at B. And then last one is a single force or a resultant. And that's somewhere in the beam that would produce the same vertical reaction load as all of those four forces and the same moments at A and B. Okay. And we should be able to do all of that. Just notice, since the support reactions are not included, the given system will not maintain the beam in equilibrium. That's fine. Okay, so here's our strategy. The force part of an equivalent force couple system is simply the sum of the forces involved. Okay, so if you remember what we were talking about before, we've got a force when we're looking at our, sorry, I'll go back one more slide. If we're looking at our little our little beam here, well, our little peanut, we've got three forces here. Yeah, they're not concurrent forces, but they're all being applied about an origin. In this case, we're trying to make our origin A, and then in our second part, we want to make it B. Okay, so when we do that, we're basically summing up all of the force vectors and all of the moment vectors. And we get a single resultant force that's equivalent to all of our forces being applied, and a single moment vector that's equivalent to all of the moments being applied. Are you guys with me?
Yes.
Excellent, Joyce. Thanks, Praveet. Nicole, yep, great. Okay, that's awesome. So let's, so here I just want to go again. The force part of the equivalent force couple is simply the sum of the forces involved. In this case, it's pretty easy because they're all in the vertical y-axis direction. And then the couple part is the sum of the moments caused by each force relative to the point of interest. So in part A, the point of interest is A. In part B, it's B. And then the last one is we're going to find a location where the single resultant force will cause the same moment about A and about B. Okay. So once you find the equivalent force couple at one point, you can transfer it to the other point by a moment calculation. Right. So here we have the working for it. Okay. So let me just annotate this. What's a nice color? Blue for this. So in this case here, we've got all of our four forces in vector notation, right? So if we're assuming that the y-axis is positive vertical, we can see that it's 150J, minus 600J, 100J, and minus 250J at B. And then over here, we've got our distances, again, as represented by in vector notation. So 1.6i, minus 600. All of this is with respect to A because part A deals with the moments about A, right? About this guy here, about A. Okay, so what we want to do is let's compute the resultant force and the resultant couple. So let's do the resultant force first. So the resultant force is going to be simply the sum of the force vectors. Yeah. Now notice it doesn't say X or Y, right? It's just saying sum of the forces because we could have I, J, and K components in other analysis. So in general, it's just saying the sum of the resultant force is equal to the sum of each individual applied force. Here we've got 150J minus 600J plus 100J minus 250J. And our resultant is minus 600 newtons J, acting straight down, okay, in the negative Y direction. So straight down. Now, you can see we can take that 600 J and apply it over here. Okay, that has no impact on our resultant forces. Okay, if we were to put our, remember we've got resultant forces here and here. The total sum of our resultant forces is going to be the same, yeah? But we're just looking at the force couple system here. Over here, we've got MRA, which is the moment about A due to the resultant R, is equal to the sum of the moment arms cross the force vector. Okay, so each individual moment arm cross each individual force vector. And in this case, because we're taking moments about A, we eliminate the 150J. So this 150J passes through A, therefore the moment arm R is equal to 0. Okay, so then we have our first vector is 600J minus 600J. So it's 1.6i cross minus 600J. Then we've got the 100J. So it's plus 2.8i. Yeah, 2.8i, 1.6i, 2.8i cross 100J. And then lastly, it's plus 4.8i cross minus 250J. Okay, now we know that I cross J is equal to
K.
Yes, K indeed. Okay, so all of this is going to be K, 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 and it's important that it's positive K. So then we've got minus 600 times 1.6, 100 times 2.8, 4.8 times 250. Then we mute your microphone, please. And the total is going to be minus 1880 Newton meters. Okay, so that is our equivalent force couple system of these forces about point A. Okay. Let me just clear that. Now, part B, let me just see if we got any questions. Excellent. K, K, K. Everyone's got K. Now we're going to do the same thing, but we're going to do it about point B. Okay. Now, so here we've got part A. Here, this is our solution to part A. Well, now we want to move everything to part B. So we want to go from A over to B. So remember, we could do this previously by just moving the force and then adding a component. Okay, and that component would be 4.8 I cross minus 600 newtons. So it would be the former one, M R A plus that, yeah? And this goes back to one of those lecture notes that we had finished where, do you remember where we had this kind of a system? We had here, and we had a force being applied here. And this was O, and this was O prime, and this was S. Well, if I move it to this side, I move my force over here, and I apply a moment. Well, if I move it to the other side, the difference is I'll have a moment here, MO, and this one will be MO prime, and M, the final one, MO prime, is equal to MO plus S cross F. And that's exactly what I'm doing here. Okay, you can have a look at those notes, but rest assured, we've had a look at this already. So part B is find an equivalent force couple system at B based on the force couple system at A. So the force is unchanged, okay, by the movement of the force couple system from A to B. So that can be done quite easily. So we're moving from A to B. And the couple at B is equal to the moment about B of the force couple system found at A. So in this case, M B R, so the moment about B with respect to the resultant R is equal to MAR plus RAB cross R. So in this case, we've got minus 1800 K plus minus 4.8 I cross minus 600 J. Okay, so then our MRAB is equal to 1000 Newton meters. Okay, and that can also be derived if we go back and apply the same process in part A. We could do the same at B if you wanted to, but this time you'd be taking moments about B. Okay, so if I wanted to, I could apply this equation here. I can apply this equation here, or I could go back here and do the same thing here, but I would go, let me just, I could go and apply everything at B, and that would be minus 600 newtons J. And instead I would have, so this is 4.8 I, so I'll have 4.8. This one would be 2 0.0 I, this guy, and this guy here would be, what's that, 3.2 I. Okay, so then our MBR would be equal to sum of R cross F. Yeah. And then this time it would be, what do I have? I got 2.0 I cross 100 J. That make sense? Yeah.
Yes, sir.
Okay. And then I have plus 3.2 I cross minus 600 J. And then I have plus 4.8 I cross 150 J. And so that would be equal to, what's that? That's 200 K plus 3.2 times 6. What's that one? 3.2 times 600.
1920.
1920 K. And then lastly, I got, what's this one here? So that's minus, sorry. Delete that. And then the last one is 4.8.
720.
This one here, plus 720. Okay, so 720 plus 200 gives me 920 minus 1,920 gives me minus equals minus 1,000 K. Yeah? You can see we could have done it both ways, but I think you'd agree that it's simpler if you know the if you know this formula here, right? Which is really just when I shift a force couple, it's just adding the moment couple that I had before at A. I just add another moment, which is equal to RAB cross R. Okay. Excellent. Thanks for putting all the answers in there. Sorry, my screen is only so small. So if I have like cameras and I've got everything on here, I can't really see much of my screen. It's easier when I go into work. Then I got two big screens on the office computer. Okay, no worries. And the last part of this problem is the last one is the resultant of the given system of forces is equal to R, and its point of application must be such that the moment of R about A is equal to MRA. This equality of moments leads to, so now this is what we're trying to do. We're trying to find the point of application of our resultant force R that will produce 1,880 Newton meters at point A and 1,000 Newton meters at point B. Okay, so we're trying to find that position where X is located. And so here we're saying that R, which is in this case is equal to X. Okay, we're trying to find the vector R. Remember, when it's in bold, that's a vector. Okay, cross R, which is our minus 600, is equal to MRA, which is the moment that we had previously here, right? Our moment that we had here was 1,880 Newton meters. Okay, now we don't have that anymore implicitly as a couple. What we're saying is we want to put our resultant force there that would produce that moment at A. Okay, so if we do that, we're saying R cross R is equal to MRA. So then it's XI, which is the unknown distance, cross minus 600J is equal to minus 1,880 Newton meters K. So then I've got this form, and then all I need to do is X is equal to 1880 divided by 600, and I get x is equal to 3.13 meters. So if this is 3.13 meters, I'm going to produce a negative moment here equal to 1880. And I should also, if that's 4.8 at the other side, this distance here is, what's that? 1.67, yeah. And if I've got 1.67 times 600, that should give me 1,000, right? Over here. Yeah. And I think you can perform that calculation yourself and see that that would work. So why was the answer where? Last example. Yeah. Plus 1,000. What happened? What happened, Dwayne? No, it's minus 1,000. Why is it minus 1,000 here? It's still plus 1,000 here. This distance is 1.67. Okay. And so the moment is still going to be plus 1,000. So you got it. Well, I went through it rather quickly, but if I'm taking it about point B, remember it's no longer plus I. It's going to be minus I. Yeah, it'll be minus 1.6. So minus 1 time, well, minus 1.67. Sorry if I'm skipping things, but if I'm going in this direction here, this is going to be minus 1.67 times minus 600, so it's going to give us a plus 100, yeah? So why minus 4.8 for R in B? Because the distance R about B is directed in the negative x-axis. Yeah, that's what I was just talking about right now. Yeah. So if I go back here, so this is a minus 4.8 because I'm taking moments about B. Yeah. So I'm going in the negative x direction. No worries. Okay, so how do we get the 600 in part? 600 SN, bro. You gotta pay attention, man. The 600 is the same force that we had, like that we've been dealing with from part A and part B. The 600 is the resultant, right? So now we've got the resultant from part A, the resultant from part B. It's the same resultant. Now we want to find that resultant, the location of that resultant where it will produce the same moment that we did from part A and the same moment that we had in part B. Okay, it's an equivalent system. So the question asked us, you must pay attention, guys. So the question asked us, for the beam, reduce the system of forces to a single force or resultant. Okay, so no more couple. Okay, but that doesn't mean that the moment doesn't exist. It just means that the force location will produce that moment. Okay, there's no pure moment being applied. Pure moment being a couple. Okay, so that 600 is the same 600 that we had from part A and part B, which is the resultant force on the system. Okay, guys, well, that's the end. That's the end of chapter 3. my work here is done. But we've still got time left here for sure. So I think I wanted to cover quiz 1 solutions, unless you guys have got something else you want to talk about. And then tomorrow I was thinking maybe we could go over some sample problems. We could do some problems in relation to chapter 3. Yeah. Okay, so let me go through my solutions for quiz 1. We'll start with question 1. I think you guys have seen your marks now. They're out on Moodle mark sheet. Okay, so, and as I was explaining before, what I was saying is that I'll run a second quiz this Saturday night, and then we'll take the best. I'll take the best mark from quiz 1 and quiz 1.1. I'm calling it, because it's not quiz 2. Quiz 2 is going to be given by Jay in the next session. Huh? No, it wasn't. It wasn't deducted, Sahil. So if you entered in 2 decimal places, the error factor. So the way these questions work is I put the solution to 3 decimal places, and then I give it an error band. Okay, so if you're too far outside of the error band, it's gone. But that's why I told you you should enter your solution to 3 decimal places. So here is so this is question 1 from the quiz, yeah? So it says determine the X and Y components for each of linear. Still in chapter 2? What do you mean? Of course we're in chapter 2 for the quiz, yeah. It's what quiz 1 is all about, okay? I can increase it to chapter 3 if you want. Let's do it. Linnea wants chapter 3 as well.
That'll be all right.
No, I think let's do it. Let's do chapter 3. I like the way Linnea thinks. Everyone can thank Linnea for that excellent suggestion. So quiz 1, let's determine the X and Y components of each of the forces. In general, this was done pretty well. I think where a lot of you guys stumbled was this, and it's me being sneaky, but this 3 and 4, a lot of you guys got a bit confused because it looks like it's obvious that 3 looks longer than 4, right? And a lot of you basically had done this 3, 4 because you're assuming that because it looks longer, that the triangle is kind of flipped, but it's not. Okay, it's definitely 3 and 4, and so you need to pay attention to the figures here. So this is a 3, 4, 5 triangle. So in this case, sine theta is equal to 4 on 5. Cos theta is equal to 3 on 5. Okay. Now this side will be a negative. This side will be a negative. This will be positive, negative, positive, positive. Okay. So those would be the resultants that we have there, right? So if I'm going to split this up, I've got a positive 900 cos 45 and a negative 900 sine 45. Then I have, why can't we review the quiz? Well, you could. I guess I can make it reviewable. And then I've got a plus 600, and this time it's sine 30, and plus 600 cos 30. And then lastly, I've got minus 700 cos whatever that angle is, which is going to be times 3 over 5, and then minus 700 times 4 over 5. Okay, so you can save some time if you know that. So over here you can see that I resolve the 600 force into X and Y components, and I've got essentially 600 times a half, so Fx equals 300 newtons. Okay, and that's for this one here. The X component here is equal to 300 newtons in the X direction, and Fy is equal to 600 cos 30. Yeah, X100 is 600 cos 30, which is 300 root 3. Okay, then over here I'm resolving the 900 Newton force. Okay, so if I do that, that one's pretty easy. So I've got whole numbers. Yeah, you can put 300. You can't put 300 root 3. So I actually put in the decimal in there. But if I was doing this by hand, I would, like, if I was submitting a piece of paper, and if I were you and I was submitting a piece of paper, I would have just left it at 300 root 3. It's also helpful if you carry that through to your calculation. And when you're doing your final resultant calculation, you use 300 root 3 rather than the decimal, because then you're already kind of got some calculation errors and rounding errors. Okay. So then I've got, this is our 900, this is 45 degrees. So this is going to be 900 plus 900 cos 45, and this is minus 900 sine 45. And some of you put in negatives, some of you put in positives on both, and you neglected the negative sign. Okay, so don't ever do that. So that's equal to 900 on root 2, and this is equal to minus 900 on root 2. Okay, so that's how you split that one up. And then lastly, we've got the 700 newtons here. So 700 is in the negative X direction, sorry, in the negative X direction and the negative Y direction. And this is a 3, 4, 5 triangle, right? So this is 3, 4, 5, and 700 newtons. So if I'm looking at theta there, this is going to be 700 times cos theta, negative, and this will be negative 700 sine theta. And then that will be equal to negative 700 times cos of theta will be 3 over 5. And this will be equal to minus 700 times sine of theta, which will be 4 over 5. Okay. And so you'll end up with minus 420, and Fy is minus 560. Yeah. Then the X component of the resultant forces is equal to the sum of all X component forces. So I've got 300 plus 900 on root 2 minus 420. So the answer you should have got is Rx is plus 516.4 newtons. And Ry, similarly, will be equal to minus 536.4 newtons. I think I've got something wrong in there. Sorry, I think I mistyped something there. So this is meant to be 676.8. But don't think I made that mistake in the quiz. So then I have my resultant will be 851.3 newton, okay, which will be the square root of the sum of these squares. So that's the final answer there. And then lastly, you've got alpha is equal to 810, and you'll notice you've got to pay attention to the way the quiz is formatted. So some of you had a negative sign in here, some of you had positive, but it says essentially our direction is not given by the sign, it's given by, it was the direction. So it's to the right and below the horizontal. Okay, so I'm looking for that angle, and then this determines the direction. Well, in this case, you can see that the direction is given by Rx is positive and Ry is negative. So therefore the resultant, so that's Rx, that's Ry. So our resultant is to the right and below the x-axis. Yeah, like that. That's alpha. Okay, so that is that. Let me bring up quiz 2, or question 2. Where's question 2? Here's question 2. So yeah, we got our toy rocket. Formatting. We've got 3 cables, AD, AC, and AB. They're all connected at A, and this rocket, this little rocket is pulling up. This is a problem that I think we've kind of seen already. It's just a little bit of a different one. The one that we did in the tutorial was it hanging from the ceiling, remember? At 3 points, and you had to work out the force that was being generated. So here it says, there was the blow up balloon in the tutorial. The balloon was the worked example that I did, Dwayne. Daryl, can you mute your microphone, or someone? I can only see Daryl, looks like he's unmuted. Yeah, the blow up balloon, I think I did that as a sample question, Dwayne. So here we've got the rocket, and in general, I think, yeah, the highest mark that was gotten for this was 42 out of 60, and the last bit was 44, could have been. So there were some good attempts at it. The last step was kind of bungled in the end. Okay, so here we've got all of our geometries there. Yeah. So our governing equation, or our equilibrium equation, is our sum of the forces is equal to 0, is equal to the tension vector AB plus AC plus AD plus PJ, right? PJ being the rocket being applied vertically upwards. Okay. Now, something that in the next quiz that I'm probably not going to do is I'm not going to lead you as much with all of the different steps. I'm going to like say, hey, let's do this part here, and now I want you to tell me, you know, what this step is. You know, show me that. So I'm going to skip a bunch of steps in between, and then I'm going to jump ahead and say, hey, tell me what this is right at the end. Okay, because I think I gave you fair. I kind of gave everything. That's why the marks were so high for that last question, because every time you put a data entry field, that's like, it's a minimum of 1 mark. Okay, so that's why there was like 60 marks for question 2, because I put in all of these fields, and this time I'm not going to put in as many fields. So I'm going to skip a few steps, and you're still going to have to do the problem, but then I think what it'll do is it'll avoid you having to put so much data entry and save you a bit more time in quiz 2, right? Because you have to like do the whole thing, then you have to go and enter all the data, right? And you end up running out of time. So let's kind of fix that issue in the second quiz. So yeah, so the vector for each cable, and again, we're taking basically particle equilibrium about A. Yeah, so we need to work out the vectors. Why do we need to know the vectors? Well, because we're applying this equation. Okay, this is the equation that we're doing. So over here, this equation, we need TAB, okay, which is equal to TAB times lambda AB, which is equal to TAB times A to B, the vector over that. So we need all of these components. We need to find TAB, we need to find the vector AB, and we need to find its magnitude, all right? So we need to find all of those things. That's why we're here. So then we go, we need to know the vector for each of these cables, okay? And So on that, I know quite a few have got this right, but if you'll bear with me, so AB, we're going from A to B, yeah? So that's the direction that we're headed in. So if I want to go from A to B in the X direction, I go negative 150. You can see here is the 150 over here. So I go negative 150. Then in the Y direction, I come down negative 500. Well, that's right. I come down negative 500. So minus 500, that's this here. And then I come across minus 300. Okay, and that's this dimension here. And that's how I get here. I get minus 150, minus 500J, minus 300K. Yeah, you guys with me on that? Then to get to C, I'll just do one more. I have to come across over here, positive 450, positive 450 in the I direction. That's this guy here. Then I have to come down minus 500, minus 500. Oh, sorry, plus 500.
Minus.
Yeah, sorry, it's minus 500. It would be like as if I didn't do this, right? And then I have to come across plus 100, sorry, plus 100 here, yeah? Okay, so, and that's here as well, right? So plus 100, okay? And that's how I get here, 450 minus 500 plus 100, okay? Are we all good on that?
Yes.
Okay,
Yes,
great,
sir.
great.
Yes, sir.
Excellent, excellent. And then simply, we just work out the square root of the sum of the squares, and we get the magnitude of each of those vectors. Why do we need that? Because what we're trying to get to is our unit vectors, yeah? What we're trying to get to are our unit vectors here. Our unit vectors because t, the vector, times the magnitude multiplied by the unit vector. Okay, so that's the reason. Remember, we always, you know, these are the different steps, but we need to remember our end goal. If we can understand what our end goal is, well, then we know all the steps that we have to follow, right? So a lot of you, and I've noticed this about our students, is that you guys get caught up in, oh, this question that you've never seen before. You go, how do I do that? Well, if you're not thinking about necessarily the process, but if your process can be, I start with my end goal, this is where I want to get to, then I need to fill in the steps, yeah, to get to that point. Okay. So some of you see the trees and not the forest, and some of you can see the forest, and then you can work out the trees, yeah? So now we've got represented by the magnitudes multiplied by the unit vectors. Then I substitute into equilibrium equation and factor in I, J, and K. Okay, so this equation here is our first equation up the top. It's this guy here. Yeah. So essentially I substitute it into there, then I gather I terms. So I gather I terms, J terms, and K terms. So then I've got the I term from TAB. Let me just do that. I've got that I term there. I've got the I term from TAC, and I've got the I term from TAD. Can you guys see that? Then I've got the J term, the J term, the J term, and the J term, right? And then lastly, I've got, oh, sorry, right, this guy here. This guy here. Okay. And then lastly, I've got, looking for another color, the K terms, yeah? K, K, K. What I've got here is all my I terms form the sum of fx. All of my J terms form the sum of fy. And the last one is sum of fz. And I'm going through the solution now, mate, so you should be writing notes on this, okay? I'm not big on giving solutions. You know why? Because when I give solutions, I can't use the question next year, or I can't use it the year after, because all of you guys go and post it everywhere. And the biggest problem that we have these days is we lose, as a lecturer, I lose all my textbook solutions. I know that a whole bunch of you guys end up sharing, well, the textbooks solutions are available for certain questions on the internet. They could be available for all of them, you know? And so I have to spend time like making these questions, and it's not a, okay, so what I always say is, if you want the solution, watch the video. Okay, I'm not going to post it anywhere because, you know, that's just lazy. If you guys really want to know it, do the work. So the same thing with the tutorials. People are asking me questions. Oh, sir, can you release the tutorials? No, you know what I do is I give you the answer. If you have a solution, show it to your tutor and we can work through it, right? But if we just give you all the solutions all the time, I don't know whether you guys will ever do any work. Yeah, and think you know how to do it, when in actual fact, you have no clue. You're just good at copying a process. You're good at like doing this, but you don't actually know how to solve problems. Okay, so if you're interested in it, take notes, okay, go and work it out yourself, and then ask questions in your tutorial, or ask me when we're in a lab session or something like that, right? You know, when I'm in a tutorial session or in a lab session, it's a 3-hour lab session, but it's done in 30 minutes. You have, and there'll be one person that'll say, oh, can you help us with this tutorial? And no worries, I'll help you. But if you don't have any questions, like, man, I'm not going to give you solutions. You think I'm the kind of person that volunteers solutions? Come on, man. So then over here, for equilibrium, we can then set these coefficients to 0. So essentially, I've got fz equals to 0. I've got fy equals to 0. And represented here. Okay, so I'm taking each of these. And I'm equating them to 0. So now you can see I have 3 simultaneous equations, right? 3 simultaneous equations, but we know that TAB is equal to 20 newtons. So we know TAB, this guy here, we know him. Knowns, TAC, TAD, and P. So what I want to do is I can solve equation 1 and equation 3 simultaneously, yeah? So that's the next step. The next step is here, I solve equation 1 and 3 simultaneously. Okay, so I've got 2 unknowns, I substitute in for TAB, and I end up with equation 3 prime, so I use 3 prime. 3 prime, this equation here, I rearrange it for TAC. So essentially TAC, I've got 0.147 TAC is equal to 9.97 minus 0.311 TAD Therefore, TAC is equal to 1 over 0.147 times 9.97 plus, minus 0.311 TAD. Okay, so now I've got a form for TAD, and I call that equation 4. And I take TAC, so that's what it says here. I take TAC and I substitute it into equation 1 prime. So I take TAC and I put it back into our previous equation, right? So I substitute it into 1 prime and I get 0.662 times all of this, okay? So when I evaluate TAC, this is what I get. I get 67.77 minus 2.12 TAD. So when I solve this, and this was, so this, all of this part here, this, getting that solution, getting TAC, this was worth like 5 marks, and the last one was worth 6. So in total, you can see there's quite a lot of working in here, right? There's quite a lot of working in this section here. And so that's solving simultaneous equations, which is something that you guys should be very familiar with in your maths subjects, okay? So in case you didn't know, you've got to be good at maths to be an engineer. So when you get that, you end up with TAD over here is equal to 28.446, and TAC is equal to 7.53. Now we've got all of them, right? We've got TAD, we've got TAC, we've got TAB. All of those are worked out. So we can substitute all of those into equation, I think it's equation 2 above. We go up, yeah, it was equation 2. I think I typed that wrong. Try and line that up again. Yeah. So you substitute it into equation 2 above, which was 2, and solve for P, the 291 newtons. Okay. So no one got through this properly. Okay. And that's how you do it. That was question 2. Any questions, guys? Negative, sorry, what are we talking about? Negative, Alfredo, the rocket goes upwards. Why do we use a negative J? I don't think we did use a negative J. Over here. It's up here, it's a positive PJ. Positive PJ up here. Who got the highest mark? That's none of your business, Dwayne. Again, JN. You can go and review the this video when they put it up, but essentially you should write down these numbers. I really don't understand why you guys aren't writing stuff down. Like, write down TAD, write down TAC. I hope you're writing it down. Then go and do it for yourself. Yeah. I think you guys are getting too used to being spoon-fed, you know. You guys need to start doing your work, getting into the textbook. You know, there's so many questions in the textbook that you could be doing, that you could be attempting. Yeah, don't wait for me.